Hello everyone, and welcome to this session of Distributed Edge Cloud Architecture for Generative AI. The rapid advancement of GenAI technologies has generated an immense amount of new digital data on the internet. This surge poses fresh challenges to existing computational and network frameworks. Originally, AI-driven services rely mainly on hyperscaler infrastructures due to demands for extensive processing capabilities. However, such services may encounter elevated latency levels and data privacy concerns. On the other hand, edge, sovereign cloud hybrid architectures could provide both the right processing power and low latency together through coordinated efforts between edge devices and sovereign cloud services resources. By deploying computation at the edge alongside end-user equipment, latency can be reduced through locality of data and operations. Meanwhile, sovereign CSPs data centers offer scalable, high-performance virtual infrastructure to support intensive AI workflows. In this video, we'll explore the GenAI distributed architecture and the value proposition for Dell Technologies in this space. Generative AI autonomously produces images, audio, text, and 3D objects that mimic human work. GenAI now enables many applications like image creation, text-to-speech, chatbots, and augmented reality. Recent GenAI models rely on deep learning methods like generative adversarial networks and large language models. However, these complex models require powerful centralized computing infrastructure due to their huge size. Users experience high latency when cloud servers face heavy traffic volumes. This limits GenAI for applications requiring low latency. The centralized framework is unsustainable as generative models continue advancing. New solutions are needed to handle next-level generative AI at scale in a distributed manner. GenAI poses unprecedented challenges to scalable computing systems and the need for edge cloud computing because of the following reasons. One major challenge is the vast amount of data generated when GenAI autonomously creates multimedia content like images, audio, and text. Compared to traditional AI, GenAI outputs have much higher dimensions and require transmitting huge volumes of data. With millions of users making requests daily, current cloud infrastructures struggle to efficiently handle this traffic load. Power consumption is another pressing issue, as cloud data centers need massive amount of electricity just to power the GPU servers. For GenAI specifically, the power needs are even greater since complex neural networks must be routinely trained on new data and then used to process user generation requests in real time. This level of cloud computing is unsustainable from an environmental and economic perspective. GenAI model sizes are also growing at an unprecedented rate, with some neural models doubling in capacity every 6 months. This phenomenon, sometimes called Moore's Law for AI, far outstrips the typical 2-year doubling of compute power from hardware advances. If left unaddressed, the gap between required computing and available resources will widen to a breaking point. Maintaining user privacy is an additional hurdle, as personalized generated content could leak sensitive information if not properly controlled and anonymized. Federated learning provides one solution by training models across decentralized devices and edge servers instead of sending private data to a central cloud. Finally, keeping GenAI services updated with the latest datasets and capabilities is immensely challenging given the resource-intensive nature of retraining large neural networks. While cloud-based batch model updates are inefficient, edge computing opens up opportunities for distributed online learning techniques that can incrementally optimize GenAI algorithms at scale. Addressing these interrelated data, power, scalability, privacy, and recency issues will require innovative cloud edge architectures optimized for GenAI unique computational profile and future trajectory. Doing so is crucial for widespread real-world deployment and value realization. Training and deployment of GenAI services should be considered separately. For the training of GenAI models, a large amount of computational resources and training data are needed. Due to rich computation resources, sovereign cloud servers can store and run large models to process high-level tasks. In contrast, edge devices are mainly responsible for low-level pre-processing tasks. After models are trained, it's desired to deploy them on user devices for lower latency and power consumption. There are three main considerations: lightweight models, minimizing latency through edge cloud collaboration, and multimodality content generation and interface. By properly dividing the inference tasks to edges and the cloud, inference latency can be largely reduced through edge cloud collaboration. Multimedia content will become the main media for humans to acquire information, as shown by the popularity of videos on the internet nowadays. Edge cloud computing can provide personalized GenAI models. While training a GenAI model requires a large amount of data, personalization can be achieved by fine-tuning the trained model with a small amount of user data. First, an advanced GenAI model called the foundation model should be trained in the cloud with common data. To achieve personalization, personal data such as user logs and metadata are collected from user devices and sent to edge servers. The foundational model is also placed in edge servers for personalization. Then, a fine-tuning technique can be developed to shift the model domain from a generic one to a user-specific one using personal data. Typically, fine-tuning requires much fewer computation resources, and it can be entirely conducted in edge servers. From a Dell perspective, it's crucial to recognize that a generative AI outcomes entails more than just a standalone large language model. It includes a comprehensive system comprising data, infrastructure, compute, storage, and networking, software tool chains, and service ecosystems. Furthermore, it extends its impact to client devices used by AI algorithm developers. Providing engineers with underperforming client devices can impact their work, while data protection becomes clearly critical when considering the value of a trained AI model that drives a business. Safeguarding and ensuring the integrity of such valuable data is of clear importance. Our objective as Dell is not limited to creating individual components or new AI technologies. Instead, we strive to bring together an ecosystem that makes all the necessary elements for achieving AI outcomes easily accessible and readily available. Moreover, we understand the importance of enabling this ecosystem to operate wherever it's needed. In the early stages of AI, many tools were exclusively, in fact, run as cloud or public offerings, which presented challenges. Entrusting data to a shared environment devoid of regulations poses a lot of risks. Establishing an infrastructure that allows you to maintain control over your proprietary and confidential data is crucial. Dell's focus lies in validating design, developing reference architecture, and integrating systems, thereby relieving you from these burdens and allowing you to concentrate on matters of significance. Ultimately, our goal is to provide you with an expedited path to conducting AI, empowering you with accelerated capabilities. Thank you.